Hello everyone, it's David again, and we are going to talk about the Supernode today. Sorry I haven't been around for a while, but I'm hoping that I'll be able to put up these videos more often to help you out with learning how easy engineering is. So picking up right where we left off, let's take a look at this supernode problem here. As you can see, we've got four nodes. We got one here, we got one here, we got one here, and we got one here. I've pretty much already put down that this was a ground node, so you don't have to worry about that one. Alright, so we do know that we have three nodes to solve, so we can label them V1, V2, and V3. However, unlike the previous problem we did in the first video, take a look at this. We have a voltage source. We can't exactly solve this problem currently with what we know with the voltage source that we have here. So what we're going to do is turn the nodes V2 and V3 into supernodes. First we'll take V2 and V3 and we'll bring them together, like so. Cute. Next, we're going to make an equation. Basically, we're going to take the positive side of the voltage and subtract it by the negative side of the voltage, whatever nodes are connected to it. The positive side is connected to V2 and the negative side is connected to V3, and there's 5 volts in it. So V2 minus V3 equals 5. Simple enough. And that's for this node. So now we got 2 more nodes left, and we're going to treat this like a regular nodal problem while remembering one thing. V2 and V3 are one node. However, the nodes that surround it and that are next to it still treat it as if it's its own separate node. Like for example, the R1 and R2 is connected to V2, not V3, and R3 and R4 is connected to V3, not V2. So let's do this node first, so that we can get the hard part done. We know that there are 4 tunnels that are leading to this particular supernode, and we have to put all of them in there. So the first thing we're going to do is do the R1 first, V2 minus V1 over 2K. Next R2, V2 over 2K. As you can see here, these are the 2 nodes on the V2 side. Now we'll do the 2 nodes on the V3 side. So we will add them in, V3 over 2K and V3 over 2K. Since they're the same thing, we're going to combine them and we'll make it equal 0. Alright, that takes care of that part. What's next is that we're going to work with the other node, the, non-supernode. So let's look at this node first, and we will take V1 minus V2 over 2K on one end, and we will make it equal to 0.003. Remember, what comes in must come out. What's going in equals what's going out, as I've stated on the first video. Alright, now that we've done that, we can start solving it. So the first thing we're going to do is we're going to get rid of these 2Ks. Since they're all a common denominator on the second and third equation, we can get rid of them by just simply multiplying by 2K. Remember that it is not 0 on the third equation, it is 0.003, so that too must be multiplied by 2K. And we receive the following. V2 minus V3 equals 5, V2 minus V1 plus V2 plus 2V3 equals 0, and V1 minus V2 equals 6. And just a quick reminder, this third equation here, we multiplied 0.003 by 2K. Remember, it is not 0. Is not like the second equation. Alright, so we can finally combine terms like so and format it the way that we need it to do Cramer's rule. And once we're done with Cramer's rule, we come out with V1 equals 11.33 volts, V2 equals 5.33 volts, and V3 equals 0.33 volts. Supernode problems are good for multiple node problems that involve lots of voltage sources and really crazy designs. I like using it myself. You can only use it though on voltage sources that are not connected to ground. So I'd like to thank you all for watching. Please rate, comment, and subscribe. Those of you that have messaged me, I'm sorry for taking so long. These are going to be my next 5 videos though. We're going to look at mesh analysis and then super meshes on the analog side of engineering, and then we're going to start delving into the digital side of engineering with number-based conversions, Boolean algebra, and Carnot maps. And with that, this is David saying so long, and I'll see you next time.